The content presented is offered through Statistica Hub. Your support sustains Statistica Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistica Hub platform at www.statisticahub.com.
Hello everybody, welcome to our third lecture of Bayesian inference. In second lecture, we have discussed about one-dimensional and two-dimensional random variables and the probability distribution, density functions corresponding to them, and also if we are having a joint distribution functions, how to find out the marginals from that. Okay, and also the conditional distribution parts. Okay, so that's what we have discussed in the lecture number 2, and in this lecture we'll be discussing about truncated and mixture distributions, as you can see on the screen. Okay, so before discussing these distributions, let's just do one more thing, that is expectation of a random variable, which is also a very important topic. Okay, so yeah, talking about expectation of a random variable. Expectation of random variable if you are having x, which is your random variable, and when we say that the expectation of a random variable x, we actually mean that the expected value of random variable x is a weighted average of all possible outcomes. Weighted average because corresponding to each random variable we find out the probability, right? And that probability we find out for each random variable in discrete case, basically that means that probability is my weight to that particular value of a random variable. Okay, now if I write down the formulas corresponding to it, then in discrete case it will be summation x into f of x, right, for discrete, and in continuous case it will be minus infinity to infinity x f of x into d of x. This is for continuous case. Okay, and we say that the expectation of x exists if I am having that expectation of mod of x exists. That basically means that if you are having an absolutely convergent value. Okay, absolutely convergent means we can define it that my expectation of mod of x has to be absolutely convergent. That means from minus infinity to infinity, if I am having mod of x f of x into f of x into dx, now I know that f of x is always greater than equals to 0 because it's probability. So that is mod of x f of x into dx, right? That is actually expectation of mod of x. So this has to be convergent for my expectation of x to exist. Same you can define it for the discrete case, that you are having same kind of condition. Okay, f of x, so that this has to be less than infinity, right? So that is the condition for the expectation to exist. Now the next thing, let's just see some very basic properties of the expectations. Okay, that you must have already studied, but yeah, let's see one more time. So the first thing is, if you want to find out the expectation of some function of random variable, that will be equal to, in discrete case it will be summation x g of x into f of x, right? And in continuous case it will be minus infinity to infinity g of x f of x into dx, where f of x here is my probability density function, and in discrete case it is probability mass function. Okay, Here it is PMF and here it is PDF. Okay. Second thing, that the expectation of sum of two random variables is equal to expectation of x plus expectation of y. Next thing, expectation of Cx is equals to C into expectation of x, where C is any constant. Okay. Expectation of a constant term is always equals to that particular constant term. Okay. Now the next thing, which is expectation of x raised to the power r, that we can evaluate by same formulas that we have noted in first point, that it will be minus infinity to infinity x raised to the power r f of x into dx, and this is said to be the rth moment about origin. About origin, which is denoted as mu r dash. Okay, now what does the term moment mean? Moment is basically a tool in the statistics which is used to describe how the data is spread out. How the data is spread out. So in this particular case, we are seeing that how the data is spread out about origin. Similarly, we can calculate the movement corresponding to expectation of x minus expectation of x raised to the power r, which is minus infinity to infinity x minus x bar to the power r f of x into d of x, which is rth movement about mean. So here we are checking that how the data is spread around mean, that is denoted as mu r. And similarly, you can check corresponding to any constant term a, that what is the spread of the data around this point a, and you can calculate this by using the same expansion. Okay. Yep. Okay. Now the expectation of x, that we use expectation of x, which is actually my mean, and that is also denoted as mu1 dash. Okay, and the variance of x, it has the expansion like expectation of x square minus expectation of x's whole square, that is also said to be mu2 dash minus mu1 dash is whole square. Similarly, there are other formulas also in the movements that are for kurtosis, for measuring kurtosis, for measuring skewnesses. These all the formulas are derived from the help of movements. Okay. Now the next thing is that we are going to see is that next property, that if you are having x and y which are independent, then the multiplication of the expectation of multiplication of two random variables is equals to expectation of x into expectation of y. Next thing, if you are having some function g of x which is equals to ax plus b, then the expectation of this function gx would be equal to a expectation of x plus b. And if we are doing g of expectation of x, okay, g of expectation of x, that would also be equal to a expectation of x plus b, not g of expectation of x, that would be g a expectation of x plus b. Okay, now let's see the other things, that from this we can say that for linear functions, this is the implication, that expectation of a linear function is the same as linear function of expectation. Okay, but this thing is not true for non-linear functions. Okay, give me a sec. Yeah, sorry about that. Yeah, now next point, that if you are having variance of ax plus b, okay, now the variance of ax plus b is equals to a square variance of x. So from this we can say that variance is independent of change of origin, but not of scale, not of scale. Okay, now let's just see the first thing, that is one more thing, which is covariance. So talking about the covariance, what does a covariance means? Okay, so covariance indicates the relationship between two variables. Whenever we are seeing the relationship between two variables, we are talking about covariance. Okay, relationship between two variables. Okay, so what does it actually interpret? If you want to do the interpretation of a covariance, how would you do it? Okay, so the relationship between two variables whenever one variable is changing. Okay, whenever one variable changes. Okay, so covariance actually measures the direction of relationship. Like if you are having a positive covariance, okay, this means that both variables tend to be higher and lower at the same time, to be higher and low at same time. And if you are having a negative covariance, then this means that the both variables are opposite on each other. That means if one is getting higher, then the other is getting lower, right? That is for the covariance signs that we have. Now how to calculate the covariance? You will be having the covariance of two variables x comma y, and the formula is expectation of x minus expectation of x, y minus expectation of y, right? And similarly, if you expand it further by 2 or 3 steps, you will be getting same thing just by multiplying the terms, expectation of xy minus expectation of x into expectation of y. Okay, and if you are having x and y which are independent, in that case the covariance of x comma y would be equal to 0. Why? Because if the expectation if the x and y are independent, then in that case I will be having expectation of xy is equals to expectation of x into expectation of y. So if I will put that here, I will be getting covariance as 0. Okay, now the next things, these are some basic properties, that the covariance of ax comma by is equals to ab covariance of x comma y. Okay, covariance of x plus a comma y plus b is equal to covariance of x comma y. Covariance of x plus y comma z, where these three x, y, z all are random variables, then it will be x comma z plus covariance of y comma z. Next thing, covariance of ax plus by comma cx plus dy is equal to ac variance of x plus bd variance of y plus ad plus bc covariance of x comma y. Okay, so these are some basic expansions. Okay, and similarly you can also write down the formula corresponding to you can say linear combination of variances. Okay, let's firstly now note down for two variables. So the variance of x1 plus x2, if your x1 and x2 are not independent, in that case it will be variance of x1 plus variance of x2 minus twice covariance plus twice covariance of x1 comma x2. Okay, and if you are seeing this thing in the linear combination, then it will be variance of summation I is equals to 1 to n Okay, AIXI, that will be equals to AI square variance of xi. This is just the generalization of what we are doing. Okay, and twice summation, this is for I x j I j, for I less than j, AI aj covariance of xi comma xj. Okay, now other thing, that is conditional expectation. Conditional expectation. Now when we are talking about conditional expectation, we are talking about how to calculate expectation of y given x is equals to x, these kinds of things. Okay, so for this, when we are doing this thing in the discrete case, you will be doing summation y, probability of y given x is equals to x, and in this case you will be doing minus infinity to infinity y into f of y given x into dx dy, sorry, dy. Okay, now we know how to evaluate these things. F of y given x, f of y given x is the conditional distribution, and we can open it as f of y given x is equal to f of x comma y upon f of x, right, by using this. Now there are some points corresponding to this also, that the expectation of x given y is equal to expectation of x if x and y are independent. If x and y are independent random variable, then expectation of x given y is equal to expectation of x. Next thing, variance of x is just the combination of two things, which is expectation of variance of x given y plus variance of expectation of x given y. Okay, yes. So these are some very these are the basic properties that we use to see of the expectations. Now let's move to the parts that we are here to discuss, that is truncated distributions. Okay, truncated distributions. So firstly, let's talking about the truncated distributions. Truncated distribution is a conditional distribution which are obtained by restricting the domain of some probability distribution. Okay, so restricting the domain means that we are talking about the values. Let's say if you are performing any experiment and if you are collecting any observations, then there are some particular set of values that they are not possible to occur in that particular experiment. So what we will do, in that particular distribution, we will apply the truncation. We will limit our domain to only those set of values which have the chances to occur. Okay, so for this, let's say consider an example. When we give the exams, okay, certain kinds of exams, and in certain kinds of exam we have an age limit, right? Let's say 18 to 30. Okay, that is my age limit. So from all the age group that I am having, I am only taking the age group of 18 to 30. Okay, so I am restricting my domain from 18 to 30. Okay, so 18 is my lower bound and 40 is my upper, 30 is my upper bound. Okay, so restricting the domain is my, and deriving the distribution on that restricted domain is my truncated distribution. Okay, and the truncated distribution arises in the cases where it is not possible to record certain values or certain range of values. Okay, or it is, you can say your data set is specific range of values, right? let's try to understand it. So in the truncation, now you can bound the values, you can restrict the domain in three ways, right? How? You can restrict the domains from the upper bound. So when you are doing, if the values below a certain limit are not observed, okay, basically means if you are doing the domain like this, that x is greater than a, you are restricting it to this side, x is greater than a, then this means you are doing the left truncation, okay. And if you are restricting the domain to x less than a, then you are doing the right truncation, okay. Right truncation means the maximum value on the right side you are putting is a. Beyond that value of a, the values cannot occur, right? It is the maximum value you are assigning to a domain is a, and after a, the experiment is not taking value after a, so you have restricted that condition, that is your right truncation, and this is your left truncation. And similarly, if you are putting the restriction on both the directions, that is said to be your double truncation. Okay, now let's see this in a normal distribution. Now we know that if I am having a random variable x which is following a normal distribution, then the random variable of the normal distribution has range from -infinity to infinity. Okay, now if I am restricting my domain of the normal distribution from, let's say, -infinity to x, okay, or I can also write it like this, that x less than -infinity, okay, then this is said to be truncated from above, right? Truncated from above, okay. And if we are doing x greater than infinity, then it is said to be truncated from below, okay. Either you say left truncated, right truncated, or either you say above truncated or below truncated, it's the same thing, okay. And if you are putting the boundation in both the directions, let's say x1 to x2, then it is double truncation. Okay, so finding the distribution on some particular range of values, particular set of values, is said to be my truncation. Okay, now let's try to understand it with some formulas. So if I am having a x which is my random variable, f of x which is my PDF, probability density function, capital F of x which is my cumulative distribution function, and I want to find out the distribution of the function x, distribution of random variable x for the set of values a less than x less than is equals to b, right? So you can find out so what we need to find out? We need to find out f of x for a less than x less than is equals to b, right? And that will be equals to f of x under the range a less than x less than is equals to b upon probability of a less than x less than is equals to b, right? I am just using the formula of conditional probability, right? And that is equals to f of x. Now I can name this thing as some function g of x, that after solving this function under the integral a to b, I will be getting some function g of x. Okay, so we have named this function g of x, which is actually after solving the this function from a to b. Okay, so upon, now what is this? Probability of a less than x less than is equals to b. That is basically my I can evaluate this probability with the help of cumulative distribution functions, that will be f of b minus f of a. Okay, so that is my distribution, the truncated distribution. Similarly, if you want to find out for the truncation from below, that is f of x for x greater than y, then what are you doing? You are calculating f of x for x greater than y upon probability of x greater than y. Okay, and I will again say that this is some function gx after solving. Okay, upon I can say that probability of x greater than y is equals to 1 minus probability x less than is equals to y. Okay, and that can be said as g of x upon 1 minus f of y, and that is my truncated from below. Okay, and similarly if you are doing the truncation from above, that means x less than is equals to y. Truncation from above means you are putting the restriction on the upper bound. Okay, so here again using the same thing I can say that it will be g of x upon probability of x less than is equals to y, that will be f of y. Okay, and this is truncation from above. Okay, we have discussed these conditions for mostly like continuous cases because we are integrating in these cases, but using the same process you can also define it for the discrete case. So if we are talking about discrete case, then let's say f is any discrete CDF. Okay, and pi is probability of x is equals to xi is my probability mass function. Okay, probability mass function, and we need to find out the distribution of x less than is equals to x, probability of x is equals to x for some, you can say for some range x belongs to a, where a would be in a set in my sample space. Okay, a is the subset of sample space, so that would be equals to probability x is equals to xi comma x belongs to a using the conditional probability of x belongs to a, and that would be equal to pi, that is probability of x is equals to xi. Okay, because the intersection would be that upon probability of x belongs to a, so that will be summation xi belongs to a of pi for xi belongs to a. Okay, so that's how you will calculate for the discrete case. Okay, now it depends that what range are you choosing, greater than a, less than a. So by using the same procedures as we do in the continuous cases, you can proceed this further for left truncation, right truncation, or whatever truncation you are doing. Okay, yes, now let's do the truncation in actually an in an actual distribution. Okay, so yeah, let's say if you are having a Poisson distribution. Okay, now in the Poisson distribution we know that I am saying that my x is a random variable which is following Poisson with the parameter lambda. Now what is the probability density function corresponding to it? That is e raised to the power minus lambda, lambda raised to the power x upon factorial x for x is equals to 0, 1, 2 and going on. Okay, now let's just consider an example. Firstly, consider an observation. Okay, that where do I need to truncate this Poisson distribution? So let's just consider an example that x I am defining my random variable as like let's take it as, I think we all go to a grocery market, right? If you are rich enough that you have someone to buy the groceries, you are lucky. But yeah, we go to the grocery markets, even any supermarket that you go, you will be standing in the line only when you are buying something, right? You will not be standing in the line of billing when you are not buying anything. Okay, so when I'm defining my random variable x, which is number of items in a in a shopper's basket, at billing. Okay, that when I'm going for a billing, how many items I'm having in my basket. Okay, now when I'm standing in the line, there is no possibility that I'll be standing with nothing. Okay, I will be having a minimum number of items, that is 1. Okay, if I'm having 0 items, then I will not stand in the line because I'm not buying anything at that time. Okay, so minimum number of purchase is 1. So if my minimum number of purchase is 1, then at that time I need to truncate my distribution, right? In the previous case, we are saying X is following Poisson distribution with the parameter lambda, where your random variable is taking the value 0, 1 and 2, like that. Okay, but here in this scenario, in this example, we can't have the value 0. So I need to truncate my distribution. Now I would say that X is following 0 truncated Poisson distribution. Okay, so here comes the truncation of the Poisson distribution, which is 0 truncated Poisson distribution, because I am having the value of X, which is 0, which will not occur in this experiment, in this example. So I will use 0 truncated Poisson distribution. So firstly I need to find out that distribution, right? So we are saying that this distribution g of x is equals to probability x is equals to x, given that your x is greater than 0, that you will at least have one item, so your x is greater than 0. Okay, now using the conditional probability, that will be probability x is equals to x intersection x greater than 0 upon probability x greater than 0, and that is equals to probability x is equals to x upon probability x greater than 0. Now if I find out probability x greater than 0, that is equals to 1 minus probability x less than is equals to 0, right? And that is my CDF. Okay, so 1 minus e raised to the power minus lambda. Okay, if I put the value and find out the CDF corresponding to the Poisson distribution, it will be 1 minus e raised to the power minus lambda. Okay, okay, now probability x is equals to x. What is the CDF? That is e raised to the power minus lambda, lambda raised to the power x, not CDF, PMF. Yeah, probability x is equals to x is e raised to the power minus lambda, lambda raised to the power x upon factorial x, and probability of x greater than 0 is 1 minus e to the power minus lambda. Okay, and that is coming out to be my 0 truncated Poisson distribution. Okay, so we will be having gxx, which is equals to lambda to the power x upon factorial x e raised to the power lambda minus 1, by just shifting or manipulating the terms. This is the PMF of 0 truncated Poisson distribution. Okay, where x is taking the value 1, 2 and 3. So I have eliminated 0 from my random variable. I have restricted my domain. Okay, so that's how we will process in the truncation. Now the concern came that when I am using the Poisson distribution, I know that what is the mean and variance corresponding to it. Okay, but what about 0 truncated Poisson distribution mean and variance? Okay, do I need to evaluate it, or is it any formula or something? So see, the main thing here is that you can truncate your distribution depending on your domain. Okay, whether you want to take your domain at s as x greater than 0, x greater than 5, whatever the domain is. So depending on your domain, you will generate your truncated distribution. Okay, and by using the same process as we do in the Poisson process to calculate the mean and variance, we can also calculate the mean and variances of the truncated distribution, just like that. Okay, so if I'm talking about the mean and variances of this 0 truncated distribution, let's see expectation of x. Okay, that is my mean. So that is x is equals to 1 to infinity, right? It is going from 1 to infinity. X into sorry, x into the PMF is lambda raised to the power x factorial x e raised to the power lambda minus 1. Okay, now I will take something common. Okay, so x and factorial x would cancel out, x and x would cancel out like this. Like I can write this factorial x as x factorial x minus 1. Okay, and this x would cancel out, and I will be having lambda raised to the power x upon factorial x minus 1 e raised to the power lambda minus 1. Okay, now e raised to the power lambda minus 1 will be a constant, and let's take lambda outside also. E raised to the power lambda minus 1 summation x is equals to 1 to infinity 1 lambda raised to the power x minus 1 upon factorial x minus 1. Okay, now what is this? This is e raised to the power lambda, so we will be having our mean as lambda e raised to the power lambda e raised to the power lambda minus 1. Okay, now this is my mean. Now similarly, let's talk about the variance. So for the variance, firstly we need to evaluate expectation of x square, that is summation x is equals to 1 to infinity x square into its probability mass function lambda raised to the power x factorial x e raised to the power lambda minus 1 is equals to. Okay, now whenever we are trying to compute these kinds of things, I am having factorial x here. Now you will not cancel out x by just like we did here, because there will be one more x in this case. So we will rewrite this equation of x square as, okay, x minus 1 plus x minus 1 plus x. Okay, if you have ever derived the mean and variances of the Poisson distributions like these, original Poisson distribution, then you must have known these procedures. E raised to the power lambda minus 1. Okay, so firstly I am going to separate these two terms, x to infinity x minus 1 lambda raised to the power x upon factorial x e raised to the power lambda minus 1 plus summation x lambda raised to the power x upon factorial x e raised to the power lambda minus 1. Now this is my expectation of x. This thing is just expectation of x, so I can put the value of this thing directly. Okay, now let's try to evaluate this. When I'm evaluating this, then summation x is equals to 1 to infinity. Okay, and I'm having x minus 1 lambda raised to the power x. Now I can open this x minus 1 factorial x minus 2 e raised to the power lambda minus 1. So this and this would cancel out. Okay, plus I am putting directly the value of expectation of x, which is lambda e raised to the power lambda e raised to the power lambda minus 1. Okay, now taking lambda square common upon e raised to the power lambda minus 1, we will be having lambda raised to the power x minus 2 upon factorial x minus 2 plus same thing. Okay, which is coming out to be lambda square e raised to the power lambda upon e raised to the power lambda minus 1 plus lambda e raised to the power lambda upon e raised to the power lambda minus 1. So this is my expectation of x square. Now we can evaluate the variance from it, that we know that variance of x is expectation of x square minus of expectation of x is whole square. Okay, so expectation of x square, this whole thing, lambda square e raised to the power lambda e raised to the power lambda minus 1 plus lambda e raised to the power lambda e raised to the power lambda minus 1 minus lambda square e raised to the power 2 lambda upon e raised to the power lambda minus 1's whole square. Okay, so this is the variance. Okay, you can simplify it further. Okay, taking e raised to the power lambda common from all the terms, we can rewrite these terms as, and yes, firstly this is the common part in both these things, right? So I can write this as lambda square plus lambda. Okay, and then dividing e raised to the power lambda, it will be 1 minus e raised to the power minus lambda, minus same thing here, lambda square upon this will be 1 minus e raised to the power minus lambda's whole square. Okay, so that's my variance of x for the truncated, zero truncated distribution. Okay, I hope that's clear. Yes, now let's talk about some continuous distribution. Normally the most common distribution in the continuous is a normal distribution. Let me change the pen. Yes, normal distribution, right? So when we are defining a normal distribution, we know that the PDF corresponding to it is 1 upon sigma root 2 pi e raised to the power minus 1 by 2 x minus mu by sigma's whole square, and this is defined under the domain minus infinity to infinity for sigma greater than 0. Okay, so we are saying that x is following normal mu comma sigma square, where mu and sigma square are its parameter. Okay, now let's talk about the truncation here. When we are saying we are doing left truncation, okay, so left truncation means that we are putting the limit on the left side. So let's say I am putting the limit x of L on the left side. So we are defining the normal distribution PDF, or we are using we are finding the normal distribution for this new domain. Okay, that will be f of x is equal to f of x under this range. Okay, under the range x of L less than x less than infinity upon same thing xl to infinity f of x into dx. Okay, this is left truncation. If you want to see it by the help of diagram, then it will be like this. Okay, where we have put it the limit here x of L, this is your mean mu. Okay, and this is the distribution of left truncated normal distribution. Okay, and that's how you calculate it. Similarly, you can calculate for the right truncated. Okay, so when you are doing for the right truncated, what are you doing? You are doing f of x under the range minus infinity less than x of right value. Okay, upon minus infinity to xr f of x into dx. That's what we are calculating right now. Okay, now let's see the expanded versions of them. Okay, that is left truncation and right truncation. Okay, now when we are studying the normal distribution, we always study the standard normal distribution. Okay, that we say that if I am having x which is following normal with the mean mu and the variance sigma square, then I will be having z which is x minus mu by sigma, and this z would follow standard normal with the mean 0 and the variance 1. Okay, this is my standard normal. Okay, and whenever we want to find out the CDF or probability under some certain range, we use this standard normal distribution. Just like when we need to find out probability A less than is equals to x less than is equals to b, we use firstly convert it to the standard normal, so that will be A minus mu by sigma less than is equals to z less than is equals to b minus mu by sigma, and by the help of formulas of CDF we can write it as phi of b minus mu by sigma minus phi of a minus mu by sigma, right? So when you are calculating the f of x for left truncation, Okay, so for left truncation you are saying that your f of x is equals to f of x under that particular range. I am not writing the range here, I'll just write it on the side. X of L less than x less than infinity, okay, and upon x of L to infinity f of x into d of x. That means this thing is basically you are finding probability x greater than is equals to xl, right? That is equal to probability z greater than equals to xl minus mu by sigma by using the standard normal, which is equals to 1 minus phi of xl minus mu by sigma, right? I can just rewrite this thing as 1 minus probability z less than is equals to xl minus mu by sigma, and then by using the CDF we have noted this thing. So my left truncation distribution would be f of x, okay, and I can write this as 1 minus phi of xl minus mu by sigma's inverse, okay, because it's in the denominator, so we are writing just the inverse. Okay, yes. Now for the right truncation, yeah, one second. Yes, for the right truncation. Okay, I don't know what's the problem. One second, let me check again. Yes, for right truncation. So when we are having right truncation, our formula would become like f of x, right, which is equals to f of x upon minus infinity to x of r f of x into dx, right? Now this minus infinity to x of r f of x into dx, we are actually talking about probability x less than is equals to x of r, okay. Now if we are finding this with the help of standard normal, we are actually doing probability of z less than is equals to x of r minus mu by sigma, right? That is equal to phi of x of r minus mu by sigma, okay. So you can rewrite this as f of x and phi of xr minus mu by sigma's inverse. That is your right truncation, okay. Now in the normal distribution, what will be your double truncation? Double truncation is when you will put the bound on upper and lower, basically on both the sides, okay. So a less than is equals to x less than is equals to b, right? So in the double truncation you would say that you are having the distribution, okay, that is f of x, okay. I'm just naming this distribution as f of y because it is double truncation, so just for different notations, okay. That will be f of x upon a to b f of x into dx, and that is equals to f of x. Now we have just calculated that what is the probability under a to b, that is coming out to be phi of b minus mu by sigma. minus phi of A minus mu by sigma. So we can write this probability distribution of this double truncation as phi of B minus mu by sigma minus phi of A minus mu by sigma's whole inverse. Okay, so these are my distributions for normal distribution, basically for double truncation, right truncation and left truncation. And if you know the parameters, if you know what is the upper bound and lower bound, you can easily calculate your distribution by just putting down some values into it. Okay, and also if you want to see the graph corresponding to it, so the right truncation is basically like this. Okay, where this is your mean mu and this is the rightmost value x of r. Okay, and in this case, when you are doing a double truncation, at that time you will be having a distribution like this, not this, sorry, yeah, where this is your A and this is your B, because you are cutting down the domain so from both the directions. Okay, that is your double truncation. Okay, so I think we'll not be able to cover the mixture distributions in this class. We'll be covering that in the next class. My pen is also having some issue, so I think we'll end up the class here and we'll discuss the mixture distribution in the next class, and also the very important thing, which is the you can say the Bayesian framework, or you can also say the difference between the frequentist and the Bayesian approaches. Like, we will be discussing these parts in detail in the next lecture. Okay, let's say whatever gets covered in the next lecture. Okay then, let's see you in the next class, and have a nice day. Thank you.